All right, so chemistry and physics is actually the first section on the MCAT. We're reviewing it second, but it's the first section that you get. And it's an interesting bag because it's kind of a little bit of everything. It's where you see general chemistry and physics the most, but biochemistry also kind of ends up here as well. Even though biochemistry has its own section, right? Like elements of biology and biochemistry get involved in this section as well. The best way I can explain it is that it's the same concepts are being discussed, but in the chemistry physics section, it's more of a focus on numbers and equations and things of that nature. Whereas in the biology and biochemistry section, it's more conceptual and it's more of an understanding of properties and relationships. There's also a little bit of organic chemistry. I know a lot of people really dislike organic chemistry. On the MCAT, the organic chemistry that you need is not that significant. It's really like just organic chemistry 1 and not like any crazy synthesis reactions from organic chemistry 2. You don't have to like memorize like reagents like as much as you would need to in organic chemistry 2. You do need to have an understanding of structures and stuff that you would get from organic chemistry 1. So that's how much you would need organic chemistry in this section. And the other thing is that it's such a mixed bag because the way that you see it here, like the weighting that we have here is just in terms of like content. But what you actually see on your exam is not strictly going to be this neat, right? It could be a little bit more heavy on the physics. It could be a little bit more heavy on the chemistry. You could get like a really tough organic chemistry passage. You never know. So the weighting that you wouldn't get like an equally fair chemistry physics section. And also the other thing is like, for example, chemistry, right? When we talk about chemistry, that's a lot of different things in general chemistry, right? We could be talking about molarity, right? And we could be talking about conversions, right? Or we could be talking about acids and bases and titrations. Or we could be talking about electrochemistry. Or we could be talking about like half-lives and radiation, right? These are all like wildly different things that are all part of chemistry. And like you don't know what concepts you're going to be tested on, right? So the hope is that you have enough time to cover everything in a reasonable degree, right? So yeah, so chemistry and physics is a lot of preparation in hopes of like not getting caught off guard and seeing something that you didn't want to see. I remember I know that I got a question wrong because I didn't bother to memorize the wavelengths of the different colors of light. I didn't bother to memorize that, the frequencies and the wavelengths of the colors of light, because I thought, oh, that's such a niche thing that wouldn't show up. Well, it showed up on my exam. It showed up and I was fuming. I was really annoyed because it was a gimme question if you knew it. But if you didn't know it, then you had to guess. So yeah, not to scare you or anything, but just to give you an idea of, this is probably the section that relies the most on memorization. No, actually, no, that's not true because psych-soc has a lot of memorization too. But this, there's a ton of memorization. You have to memorize equations. You have to memorize units. You have to memorize um, certain numbers like constants and stuff, right? But it becomes easier if you understand how they relate. And we're going to dig into that today. Remember, I told you at the beginning of all this that the MCAT is testing you on critical thinking, right? So the memorization is a stepping stone to the critical thinking, right? And we saw last week how you use critical thinking for cars, right? This week, we're going to see how you use critical thinking for numbers. It's a totally different ballgame. And we're going to look into that now. This is a big thing. You don't get a calculator on the MCAT. Most people either know this or are surprised to find out about this, right? You don't get a calculator whatsoever. So that means a number of things, right? Not only does it means a couple of things. First of all, it means that you're not going to get crazy numbers. Even if the numbers look like they're crazy, they're meant to be solvable without a calculator, right? That's one. The other thing is that if you don't have a calculator, you have to get really good at number manipulation without a calculator, right? So that's a separate skill set of its own that we're going to talk about. What you do get is a periodic table, and this is the exact periodic table that you get on the MCAT. This it gives you your atomic masses and it gives you the elements. It doesn't tell you like what element it is. It only gives you the abbreviation, but this is what you get, and this is fairly useful for various chemistry, especially like molarity type problems. Okay, so we're going to talk about units a lot, and these are just some resources where you can that have them like organized nicely. We'll come back to this in a moment. So units, right? What are units? So units are these kinds of, it's an interesting thing. In the world, right? In the world, this is a bit of a tangent, but in the world, we've kind of decided to measure some physical things and just have it be represent that physical thing. So for example, if I say like, what's mass, right? What's a kilogram, right? Well, a gram is just our definition of that physical law that things have mass, right? And the interesting thing is all of the units that we've at some point or another like ascribed to things all relate to each other and all have flexibility in if you start with one unit, you can see a relation to another unit because in our physical world, everything is related. So this is an interesting thing to kind of wrap your head around. Here, right? All of these things are describing some kind of quantity, right? Maybe it's electrical capacitance, maybe it's energy, maybe it's force, right? What we see though, right? We see so if we look at force, if we look at weight, right? The unit for force and weight is a Newton, right? But what is a Newton? What is a Newton? A Newton is a kilogram times a meter divided by second squared, right? That is what we call our SI base units. That's what I'm saying, what I mean by every unit relates to some innate physical quantities that we've ascribed in our world. So for example, we have an innate unit of length, which is a meter. We have an innate unit of time, which is a second. We have an innate unit of charge, which is an amp, or sorry, a current, which is an amp. So this is really, really interesting. This is really interesting because you can kind of mix and match these base units and create more complicated units, right? And that's back and forth, right? You can, if you start with a complicated unit like a Newton, you can break it down into its base units. And if you start with a base unit, you can turn it into a more complicated symbol like a joule, right? So for example, if you look between a Newton and a joule, right? What's the difference between a Newton and a joule? If we look at the SI base equivalence, right? What is the difference between a Newton and a joule? Starting with a Newton, how do you get to a joule? The M is squared, right? So effectively, we multiplied it by a meter, right? And look at this. Look at joules in equivalence. Newton times meter. So a joule is equivalent to a Newton times a meter. And this is reflected in the base equivalence, right? It's actually quite elegant because everything works, everything converts all the time correctly, right? So these are all things that are, if you understand this and memorize this, then you will be able to tackle any kind of problem that they throw at you because you can just break down the complicated symbols into base equivalents. And if you have the base equivalents, you can go back to, you can kind of convert into what you're looking for. And that's exactly what I'm going to show you today. But obviously, like when you see this, right, this looks very intimidating because there's so many different symbols and there's so much different base units, right? The goal is to take it one at a time, right? Learn one concept at a time. Right now, this is kind of like the broad strokes of everything that you might see in physics, right? This is a lot to, nobody could understand this all at once, right? What you would do is you would build on your concept of physics, right? So you might start with mechanics and you might start with like understanding, okay, velocity, acceleration, okay? And now I understand, or sorry, that's kinetics, right? Then you go to mechanics and then you're like, okay, now I understand that I have a meter per second is my velocity, but then I'll multiply it by this and then I'll get, force time, I'll get a force and I'll get weight. So it builds on it little by little, right? So if you try to see the relationships between things and you try to connect things, you'll have a greater understanding of how to interconvert between things. And interconversion between things is like half of this section. Okay, so like I'm saying, units and equations are relationships. That's what units really are. So a joule, right? Can you tell me what is a joule? What does a joule measure? I'm not sure if you've taken physics yet but if you've heard of a joule, like what do you think it is supposed to measure? Energy, right? Work as well. Awesome, right? So it's not just one thing, right? There's multiple things that joules can measure, right? Energy, work, heat as well, right? So energy, work, and heat, right? The joule is involved in all of this. How can it be involved in all these things, right? How does that make sense? Why can a joule equal three different things, right? Well, the thing is that there are different equations that all relate the joule. So for example, we know that work is equal to force times distance. We also know that power is equal to work over time, right? Then that's the work, some common work equation, right? Then if we look at energy, we know that kinetic energy is equal to 1/2 times the mass times the velocity squared. Then, and remember, kinetic energy would be in units of joules, right? Then we have electrical energy, which is electric charge times voltage, which would be in units of joules. Then we have heat, which is mass times specific heat times the change in temperature. Heat is in units of joules, right? But how does this work? How can it be that all these various different equations all end up as being joules, right? Well, let's break it down into their units, right? So if work is equal to force times distance, work is in units of joules, force is in units of newtons, and distance in units of meters, right? So then we get that joules equals newtons times meters. Then we have power equals work over time, and work over time is also equal to current times voltage, right? So if you have power equals work over time, that gives us power is the units of watts, and watts is equal to joules per second. And watts also happens to be equal to amps times volts. So there's all these different connections between these various units, right? We also see that joules would be equal to 1/2 kilograms times meters times meter per second squared, all of that squared, right? And then we also see a totally different equation for electrical energy and another different equation for heat, right? But all of these, if you broke everything down to their base units, you would end up getting the same thing for the joules. So it's very powerful, and being able to relate these things and understanding, like, if I see joules in this context, I could relate it to this other context, right? That's really, really important. So I'm going to walk you through what it's like to actually use units in a problem, right? Because that's really what you want to know. Like, how do I actually use this, right? So here's an example problem. Oh wait, no, this is slightly different. Okay, I'm gonna walk through the units. Maybe I should do the units now and come back to this. Okay, I want to go to the units. Hold on one second. Give me one moment. Okay, yeah, it's here. Okay, so I'm just going to jump ahead and then I'm going to come back to this. Okay, so here we have a question. A particle with a velocity of 1 times 10 to the 6 meters per second is placed within a mass spectrometer. Upon entering into the machine, it experiences an acceleration of 4 times 10 to the 12 meters per second squared. The mass of the particle is 4 times 10 to the negative 27 kilograms, and it carries a charge of 2 times 10 to the negative 19 C, which stands for coulombs. What is the magnitude of the magnetic field? My question to you is not to solve this, but my question to you is, what do you need to know to solve this? What are you missing right now that you need to solve this? Formula, right? Exactly, right? Because we have a bunch of these numbers, right? But we don't know how they connect, right? How do they connect? Where, like, how can we, that's the question, right? So if I give you the formula, right? The formula is that so the formula, right, is actually just the definition of the unit in this case, right? So it's very important to look at what the unit of the answer is, right? Because look, they all have the same units. So this T, aka the Tesla, this is your equation. This is your formula. It's right there. They're giving it to you in the unit. So that's why you need to know what the unit is, right? If you know what the unit stands for, then you know the formula. And if you know the formula, then you can work from that formula and make the numbers fit into that formula. So you're kind of building the formula from the ground up. You're doing it in reverse, right? And I'll show you what I mean by that. So let's say that you knew like a Tesla was equal to a kilogram over an amp times a second squared, right? This is the formula, okay? So now let's try to understand, what do we do with these numbers? So all I've done is rewritten it to put put the numbers that they gave us, right, over here, and the equation, right, that we need to solve, right? So first things first, what's the easiest match that you can make here, right? What number matches to the unit in our Tesla formula? Kilogram, exactly, right? Because we have 4 times 10 to the negative 27 kilogram, and then in our formula we have kilogram up top. So that's simple, right? So if we're drawing if we're drawing it out, right, we would put that fraction bar and we put kilograms up top, right? That makes sense. So now the question is, what else can we do? What else can we do? So we have some second squared at the bottom, right? And then we have this amp, right? So here's a weird problem, right? We have an amp at the bottom, but we have no such amp in our given numbers, right? So what's the deal with that, right? Well, again, right? A Tesla is a complex unit that's built up of kilogram is an SI base unit and second is an SI base unit, but amp, right, can actually be converted into coulombs, right? So the formula for amps relation to coulombs is that a coulomb is equal to an amp times a second, right? So if you know that, then you can now plug that in by substituting, right? So now you can say that a kilogram, it's instead of kilogram over amp times second squared, it's kilogram over coulomb over second times second squared, right? And since that's a 1 over second times second squared, then one of the seconds is going to cancel out. One of the seconds units is going to cancel out. That's going to leave us with coulomb over second, right? So if that leaves us with coulomb over second, then what's the next thing that we can plug in very easily, right? We can plug in our coulombs, right? So if we plug in our coulombs and our coulombs is in our denominator, then this is what we have so far, right? So far, does this make sense? that we are plugging in, we took our unit, we're starting from a unit, right? And using the unit, we're working backwards and understanding how understanding how we're building the formula from the ground up based on the units. So now what we're left with is a second on the bottom, just a second on the bottom, right? So with what we have left, we have a meter over a second and a meter over a second squared. How do we end up with a second on a bottom, right? So the question is, right, we basically have two options. Essentially, we have two options. We can either put this on the top and then this on the bottom, or we could do this on the bottom and this on the top, right? And so the question is, which one of those choices would lead us to having seconds on the bottom, right? So let's work it out, right? In the case of in the red, right, we would have meters per second divided by meters per second squared, right? So when you see something like this, right, the meters and the meters, right, are just there by themselves, right? So you can effectively cross those out because the meters over second is the same thing as meters times 1 over second, right? So the meter, since it's in the numerator, it doesn't really have any problem, right? And then this meter is also in its own numerator, right? This meter is meter times 1 over second squared, right? So then these meters can just cancel out. And that's what we want, right? Because our formula doesn't have any meters at the end. Okay, that's good. Now, what about this? We have 1 over second and we have 1 over second squared. Well, to keep your life simple, when you have a fraction, right, like this, when you have a fraction, right, flip it to the other side, right? So I have a 1 over second squared. I'm going to flip it over here. So my 1 over second, when flipped over the fraction bar, becomes a normal second. It's the reciprocal, right? 1 over second, the reciprocal of 1 over second is just second. The reciprocal of 1 over second squared is second squared. So now I have second squared over second. What does that leave me with? If I have second squared over second, what does that cancel out into? Just a second, right? Just a second by itself on the top, right? Is that what we wanted? It's not what we wanted. We wanted a second on the bottom, right? So therefore, it shouldn't be the meters over, this is wrong, right? It should actually be the reverse, right? If it's the reverse, we'll get what we want. Do you want me to work through the reverse? Or does it make sense? Make sense? Okay. So then to basically this is where we end up with, right? That our meters will cancel out. Our meters will cancel out, and then the second will go up, and the second squared will come down because we're taking the reciprocal, and we'll end up with a second on the bottom, which is what we wanted, right? And now we move on to the best part, right? So this is what we have, right? And now we have a bunch of numbers, but we have our units exactly where we want them to be, Now that we have our units exactly where we want them to be, we can start on the numbers, right? So you're going to see a lot of scientific notation on the MCAT, right? And you're going to get very used to scientific notation, and we're going to explain how to get used to the scientific notation. But basically, right, flip everything up now, right? Since we have this denominator, right, let's flip everything up again. So this 10 to the 6 when flipped up is going to be 10 to the negative 6, right? And this 10 to the negative 19 when flipped up is going to be 10 to the 19, right? So 10, if I flip up a 10 to the if I put the 1 times 10 to the 6th upwards, it's going to be 10 to the negative 6. So that's going to be negative 27 plus negative 6, right? So that'll be negative 33. Okay, and then the 19 I flipped up becomes a positive 19, right? So I have 12 plus 19. So now I have a 10 to the 12, 31, right? 31. Yeah, okay. So this is where we're at, right? So we have positive 31 and negative 33. So what does that leave us with? What does that leave us with? So we have 10 to the 31 and we have 10 to the negative 33. What does that leave us with? That leaves us with 10 to the negative 2, right? And what about our coefficients, right? Our 4 times, our 4 times, our 2 times, and our 1 times, right? Well, our 1 times is just a 1 times, so whatever, right? We've got 4 times 4, that's 16, right? And then it's divided by 2. So we end up with an 8. So this is what we have. We have 8 times 10 to the negative 2, right? 8 times 10 to the negative 2 what? 8 times 2, 8 times 10 to the negative 2, Tesla, right? And now, what if, since this is a very small magnitude, right? What if they just want it in decimal, right? So how do we convert this? Well, I will show you a handy mnemonic, which is Lars. So Lars says when you add to the power, then you move left. And when you subtract to the power, you move right. So what I mean is, let me go back here. I have, if to get rid of this, right? It needs to become what? To get rid of the 10 to the something, what should the something be? Positive, right? Okay, so if it was 10 to the 2, it would be positive. But did I get rid of it? Because that's still times 100. What if I want it to be times nothing? In that case, I want it to be 10 to the 0. Exactly, 10 to the 0. Because if you make it 10 to the 0, then it's just times 1, right? And you've gotten rid of that, the scientific notation. So for us to get 10 to the 0, so if we have a little decimal here, right? If it says 8.0, right? Our decimal, this is what the Lars mnemonic is, right? To get this to 0, right? What do I have to do to negative 2? So if I'm going from negative 2 to 0, right? How much do I need to add or how much do I need to subtract to go from negative 2 to 0? To what? Do I subtract 2 or do I add 2? I add 2, right? So the mnemonic is Lars, right? So the mnemonic is I'm adding, right? So right now, we just said I'm going to add 2, right? So if I'm adding 2, that means I'm moving my decimal left. So I add 1, and then I add 2. And by doing this, that gets me the decimal form, where this 10 is now times 10 to the 0. So that's what the mnemonic is. By looking at the power on the times 10, right? We can say, okay, how much do I need to add, or how much do I need to subtract to get that to 0? And that is the number of spaces that you'll move the decimal either left or right. And you can remember which way you're moving it based on this mnemonic of Lars. Left is for adding and right is for subtracting. Does that make sense? So this basically told us that 8 times 10 to the negative 2 is the same as 0.08. Does that make sense? Okay, cool. So this right now, it might seem like, oh, I don't like, what's the big deal, right? It's just times 10 to the negative 2. Well, it becomes a bigger deal when you're dealing with bigger powers, right? When you're dealing with bigger powers and you have to keep your grasp on the count, basically, right? Because the scary thing is, right, if you make just one mistake in all of this, you can end up with a wrong answer, right? If you just made one, for example, if I had said 30 instead of 31, right, then I would end up with 0.8 here, right? And then I would be like, there's no 0.8 in the answer choices. So where did I go wrong, right? So that's why it's very important to be very careful and have a lot of mental math tricks, because the more tricks that you have, the more familiar you are with doing it, right? The less chance of you making a silly mistake, right? We want to, because this is not just about knowing things, right? This is about knowing things and performing under pressure, right? Performing under pressure. It's not just that, like, oh, I'm good at math. It's like, well, are you good at math in a pressure, in a stressful environment, right? So to take away from that stress, we want to have as much like small advantages or like things that we can rely on that make sense for us. Okay, so that's just one, and now I'm going to show you a couple other things. But before I show you those couple other like little advantages, I want to go back to the part that we jumped over. So wait, so basically to answer this question, right, we see that the answer is A, right, after all of this, right? And notice how all the answer choices are some form of 8, right? And basically you would get this also is a hint at how the numbers are supposed to be placed, right? Because in order for you to get 8, some version of 8, you need to have 4 times 4 divided by 2. Do you see what I'm saying? Like, in order to get some kind of 8, right? The only way to do that is if you have 4 times 4 divided by 2, right? And then the question, and then this one becomes a mystery because you could put the 1 in the numerator or the denominator and still get an 8. So for the rest of that, you have to know the unit, right? But it's interesting that you can kind of get a hint just from the coefficients, right, as well. So all of it, like really looking at it from all different angles and thinking of this not as a math problem, but more of a math puzzle. Like all the unit stuff is like a puzzle in my opinion, at least how I saw it. It's like, if you know the puzzle pieces, which are the units, can you fit the puzzle together? That's kind of how it ended up working for me. So, okay, so I want to just go back real quick to what we were originally looking at. Oh, yeah. Okay, so this is also really important. So remember we were talking about critical thinking, right? So what I just showed you with the unit manipulation was a method of critical thinking for numbers, for manipulating numbers, right? And in that case, we were given numbers to plug in, right, to our equation. However, this is also a cool thing that they do, right? And I feel like this is really a test of critical thinking, is can you manipulate the equations without any numbers involved, right? Like, we're not going to give you numbers. Just manipulate the equation and the relationships themselves, right? So this question asks, if the electrical potential energy between two equal charges quadruples, describe the change in the distance between the particles. So this question is assuming your knowledge, right, of this equation, right? So this equation is given to you here. If the electrical potential energy, right, UE, between two equal charges, in this equation, the equal charges are Q1 and Q2, quadruples, describe the change in the distance between the particles, the distance between the particles being the variable r, right? So again, remember, we're thinking about, the base is your content foundation, and then when it comes to actually solving the problem, it's your critical thinking, right? So in this case, the base is, well, do you know what electrical potential energy is, right? Do you know the relationship? Okay, you know the relationship. Okay, now solve this problem, right? What happens to the distance if I quadruple the energy, right? So how do you solve this when you don't have any numbers? Well, you can kind of set up a system of equations, right? And so this is how I like to do it, right? I would set up the relationship that they had given me, right? They told me that the electrical potential energy has quadrupled, right? So that means that it takes 4 of the original electrical potential energy to equal the new energy. 4 times the original energy is the value of the new energy, right? And then I've written out, the original equation, right? For the original, right? And then we set it equal to the distance. Why? Because we want to describe the change in the distance between the particles. So we set the whole equation equal to the distance, right? Then what I can do is write the equation for the new energy and then substitute the conversion that they gave, right? That it's quadrupled, right? So I can substitute the original for the new, right? And now that's going to give me the relationship between the original and the new, right? So I can see once I, algebraically manipulate this, that we're having a coefficient of 4 on the new distance, right? But how does this relate to the original distance, right? Well, that means that because look at this. This is now equal to this. So that allows us to relate the new distance to the old distance. So that's essentially how you can understand how you can tackle these problems, right? You start with, okay, what is the conversion that they gave me, right? What is the change that they made, right? And then solve for the original, right? Solve for that variable, right? So they're saying describe the change in the distance, right? So that means in the original equation, we solve for what they wanted, right? And then we need to, in the new equation, right? We need to plug in the old variable, right? So if for the whatever conversion, whatever change they made, right? They said that it quadruples, right? So I need to insert 4 of the old one into the new equation, and solving this again and getting it to this point, right? Getting it to the point where it's equal to the R original is going to allow us to set that equal to each other, and that gives us our final value, right? That the new distance variable is equal to the old distance variable divided by 4. So the new distance is the old distance divided by 4. Therefore, the answer is that the distance was quartered, right? So this also they also try to trip you up when they include like square roots or like squares and stuff. Like, just keep a cool head and follow a strict method, right? And don't get lost in all the different numbers or whatever, right? The strict method it's a 1, 2, 3 method, right? Set up the relationship, solve for the variable in question, right? and then plug in the old variable into the new equation, and then you're good to go. Then you've got a relationship between the old and the new variable in question. Does that make sense? So you're always comparing the new relationship to the old relationship. Yeah, because I mean, it's the same thing if you compare the old relationship to the new relationship, right? Because all you're doing is describing the change between them. So I would just pick one and stick to it, right? So you don't confuse yourself. Again, you don't want to stress yourself out for no reason. But this system will always work because you're just systematically comparing the old variable to the new variable. Hopefully that answers your question. Okay, so we also have to talk about mental math, right? Because there's a lot of math that you have to do on the fly, right? That because you're not going to have a calculator, right? You're just not going to have a calculator. So I'm going to share some, math tips and tricks, right, that are helpful for mental math, right? So if you see something like this, right, 2/3 times 6 to the 10, right? If you solve this, right, if you solve this right now into decimals, right, you get 0.66 times 0.6, which is a little bit annoying to solve, right? What you can do instead is just swap these numerators. Because if you swap these numerators, now you suddenly get much easier decimals, right? And you might think like, oh, they will never give something this simple, right? But they do, because we saw it. We saw when you set up these systems of equations, it's not a systems of equation, but when you set up these equations, you have the ability to manipulate numbers in this way. So whenever you can make your life easier, you should make it easier, right? Because you don't have a calculator and this is all time, right? So rather than do 2 divided by 3, I can just swap the numerators, and then I can do 6 divided by 3, which is 0.5. And then I can do 2 divided by 10, which is 0.2, right? And then I know that 2 times 0.2 is just 0.4. That's much easier, right? The thing is that 0.66 times 0.6 is also 0.4, but that's much harder for me to do in my head, right? So you have to manipulate the numbers such that it's easier to do in your head, right? That's a big deal. So another thing that's super helpful that you're going to get into the habit so much is dimensional analysis, right? Because because we've been talking about units this whole time, right? And dimensional analysis is really the best way to keep track of all those units and not get lost, right? So especially for anything like chemistry based, where you're converting from moles to liters to whatever, right? Set up a dimensional analysis from start to finish, right? And that will allow you to account for everything, right? Because as you can see here in the example, right? How do we convert? The question is how many seconds are in one day, right? And this is, if without dimensional analysis, this is hard because we don't know directly how many seconds are in one day, but we know other things that are in a day. What do we know could be in a day? Well, we know that 24 hours are in a day. Well, what do we know could be in an hour? Well, we know that 60 minutes are in an hour. I don't know how many seconds are in an hour, but I know that there's 60 minutes in an hour. Well, how many seconds are in a minute? Well, okay, I know that. I know that 60 seconds are in a minute, right? This is dimensional analysis. Instead of jumping ahead and trying to figure out something that you're not supposed to know and that you don't know, you take it step by step by step, right? And that's going to allow you to eliminate all of those units that you don't need and end up with exactly the unit that you do need, right? How many seconds are in a day? And this is exactly how we get how many seconds are in a day, right? And also notice that this person put They could have instead put 1 day over 24 hours, right? But their goal was to find out how many seconds are in a day, in 1 day. So that means that in 1 day would be the denominator, seconds per day, right? Do you see how it's seconds per day and it's not days per second, right? So if it's seconds per day, that's telling us that we should put the day in the denominator, right? And then when we go through, we would expect to have seconds in the numerator. And we would continue with our conversion factors until we get seconds, right? So conversion factors are very important, and you're going to learn all kinds of conversion factors, right? So what is a conversion factor? The fact that 60 minutes is equal to 1 hour. That's a fact. That's a conversion factor. It allows us to convert between hours and minutes. And then we're allowed to convert between minutes and seconds, right? So conversion factors are, and dimensional analysis is super important. You're going to see what I'm talking about when you hit chemistry, because dimensional analysis is really great for keeping track of everything. Now revisiting Lars, what we were talking about, right? If you have to move the decimal to the left, you add to the exponent. So in this case, we have 12.6 times 10 to the 3. If I move the decimal to the left, I add plus 1. If I move 1 to the left, I add plus 1 to the exponent. So 1.26 times 10 to the 4 is the exact same as 12.6 times 10 to the 3, right? Also, likewise, you can work backwards. Instead of thinking about where, if I move the decimal and then I make a change here, we could think the other way. I'm making a change to the exponent. How much do I move it? So if I wanted to get rid of the 10 to the 3, I would say, okay, I'm subtracting 3 from the exponent. If I'm subtracting 3, then I'm going right. So then I would go 1, then I would go, where did my marker go? Here. So if I said I'm subtracting 3, right? And that tells me I need to go right 3. So I go 1, 2, 3, right? So this is my new decimal. So if this is my new decimal, then I've added 2 zeros here for 12,600, right? So you're gonna get really used to that, because there's almost like all the numbers are almost always scientific notation. Okay. Now, oh yeah, so this is basically again another explanation of the reason I spent so much time on this is because you're going to have to get very, very, very comfortable with manipulating numbers like this. Extremely comfortable. It has to become like second nature, because almost all the numbers you're going to see are like this, because you're going to see you know, I remember in high school, or like before that, I would never like using scientific notation, because I could just convert it into regular numbers, and that was way easier for me, right? But the problem is you have, these numbers that are extremely high in magnitude. Like for example, frequencies are extremely small, or wavelengths that are extremely large. So it's no longer feasible to not use scientific notation. You have to use scientific notation. Okay. Another cool trick, right? If I ask you what is 8% of 25, it might be a little tricky for you to think about it, right? Well, I know 10% of 25 is 2.5, but what's 8% of 25, right? Well, the cool thing is that percentages are actually reversible, right? If I ask you what's 8 of 25, if 8% of 25, you can get the answer by just simply asking what is 25% of 8, because 25% of 8 is the same thing as 8% of 25. So 0.08, if we solve this out, right? 8% of 25 is 0.08 times 25, which is equal to 2. But it's the same thing in reverse. If I just say 0.25 times 8 is equal to 2. So percentages are reversible. Another trick, right? Another really, really helpful trick is that oftentimes you're going to need to estimate numbers, right? You're going to need to estimate numbers because a problem will be set up in such a way sometimes that getting the actual number is difficult, but you can easily eliminate the other answers just by estimating. So for example, if I asked you to tell me 0.07 times 25, that's a little tricky, right? To do without a calculator. And 0.25 times 7 also doesn't help. It's still tricky, right? So then what you can do is simply estimate around it. So for example, if I said 0.25 times 7, I'm not sure, I could try 1 up. If I increase 7 by 1, then I have 0.25 times 8. Well, that's easy. 0.25 times 8 is equal to 2, right? And what if I subtract 1 from 7? Well, 0.25 times 6 is 1.5. So that tells me that 0.25 times 7 is going to be between 1.5 and 2. And a lot of times, this is enough for you to narrow down an answer because you didn't figure out exactly what it was, but you found that there's only one answer that lies between that range, right? So again, this is another way of critical thinking, another way to think critically about and try to find the answer. Another thing, right? There is no calculator. So how do you do trigonometry, right? There's trigonometry on the exam, right? Because there's angles and stuff in forced body diagrams and whatnot. So to handle that, right? What I did was I just memorized it like a table, right? For me, I'm sure like a lot of people probably just like straight memorized it, like back in high school, but I never memorized it. So I ended up just having a table in my head where I was like, okay, I know it goes from 0 to 30 to 45 to 60 to 90. And then the cool thing is that if you memorize it one way, then you already memorize it the other way because sine increases, right? From 0.5 to 0.7 to 0.9 to 1, okay? And then cosine is just the same thing in reverse, 0.5 to 0.7 to 0.9 to 1. So if I memorized one, then I memorized the other. And then you have this, right? And it's a lot easier than using like, the square root stuff, or you don't need to use the exact values is what I'm saying, right? Because this decimal version is enough for you to get close to the right answer, right? Again, we're not solving for exact answers. This is a multiple choice test, right? You're solving enough to get to the right answer, right? So that's something else to keep in mind. Then, okay, this one, if you take anything away from this whole thing, this one's really cool. I think that this one's crazy. So if I asked you without a calculator to tell me log of 3 times 10 to the 8th, right? Would you be able to do it? Log of 3 times 10 to the 8th without a calculator. Well, what if there was a way? What if there was a way to do this without a calculator, right? And there is, because log time, you can actually estimate this without a calculator, and it's actually fairly simple. The estimation trick is log times a, so this is like an example, right? If the coefficient times 10 to the b, right? If it's log coefficient times 10 to the b is going to approximately be equal to b plus point a. So if we look at log times, if we look at this question, right? 3 times 10 to the 8th, if we approximate it, that would be 8, right? 8 is the power, so the power plus the coefficient, point coefficient, right? So 8 plus 0.3. So that gives us an estimate of 8.3. What is the actual answer? The actual answer is 8.47, right? It's not a perfect estimation, but it's close enough. It's close enough that you'll be able to solve a lot of things very easily, right? So this is how you can do logs without a calculator, which is actually something you need to do because you're going to see logs, right? So for example, this is a situation where you see logs in chemistry all the time. What is the pOH of a 2.3 times 10 to the negative 4 molar solution of sodium chloride, sodium hydroxide, right? So no calculator, how do we solve this, right? Well, we have our estimation. The estimation says 2.3 times 10 to the negative 4 is approximately equal to negative 4 plus 0.23. So if it's negative 4 plus 0.23, that's equal approximately to negative 3.77, right? Negative 3.77. Now, the question is this the answer to this question? Do you guys remember what POH is? Think all the way back to Gen Chem, however long ago that was. No, no takers for Gen Chem. POH equals 14 minus pH. That's true. That's 100% correct. Do you remember what the P stands for in POH? It's no worries. It's log related, right? The P actually stands for negative log. So this is actually the negative log of OH. Yeah, negative log, exactly. Good, good. So in this case, right, we haven't solved our answer yet, right? Because what we solved for was the log, right? And the log of this is negative 3.77. So if the POH is a negative log of OH, the POH is a negative log of OH, right? So if the log of OH is approximately negative 3.77, then the negative log of OH should just be positive 3.77. Therefore, the POH is equal to 3.77, right? Now, moment of truth, right? How does our estimations compare to the actual calculated answer, right? The actual calculated answer is 3.6. This is pretty close. This is pretty close for an estimation, right? For me, this was mind-blowing when I found out about this. Like, I thought that this was amazing. So I hope it's helpful to you guys in the same way, because it's like logs used to be such a pain for me, and then like this just made it so easy, because especially because on the MCAT you don't need the exact numbers. You just need rough numbers, right? And if you have rough numbers, that's good enough to get you to the answer, right? Because you're going to see the choices on the actual test would be like close enough to, would be far enough from each other that you would be able to pick out the right one. So I really like this trick. Okay. So now let's get into, now I've shared my little secrets and tips and tricks and whatnot. Now let's get into how you can actually tackle a passage, right? That's the best part, right? That's the most interesting thing, right? And the interesting thing about chemistry physics is that a lot of the passages are designed to overwhelm you and have very little valuable information. Like, surprisingly, I remember when I was studying, right? And remember, I think I told you guys that this was the hardest section for me, right? Because I had the weakest foundation, right? So when I was studying, when I was practicing, right, I would be reading these passages and I would have no idea what they were talking about. But then when it came to the questions, I was like, okay, I kind of understand the questions. And so at some point, I was like, wait a minute, why am I wasting time reading the passage when I never understand it, right? And surprisingly, I found that you don't really need to read the passage for chemistry phys. And I'll show you an example of what I mean. Because the questions, just like we saw with that example of the units, right? The questions guide you to the answer in such a way that you don't really need to, like in cars, we saw that we need to read the whole passage and synthesize a main idea, right? But it's not so in chemistry physics. You don't need to synthesize any main idea. It's actually the opposite. You need to pull out specific bits of information from the passage that are relevant to the question, right? So reading the whole thing is kind of a waste of time when you can just go to the question and the questions tell you what you should be looking for. So going for the questions first allows you to prioritize the relevant information. Because trust me, there is a ton of information in a typical Chem Phys passage that is not relevant to what's being tested. And I'm going to show you an example of this right now. Okay, so before we start doing a practice thing, do any questions about what we've talked about so far? Okay, great. Hopefully that means like hopefully that means like it really makes sense and not that like nobody has any idea what's going on. Hopefully that means everybody's following well. Right? Because it could be either way. It could be like, no, I have no idea what to ask, or like, no, I understand everything. But yeah. Okay, so now so this should be cool. Okay. It's making sense. Okay, great. So we talked a lot about when we looked at our passages, right? I mean, sorry, when we looked at our problems, right? We looked at mostly like chemistry and physics kind of stuff, right? Now we're going to look at an organic chemistry style passage, right? And what I'm going to do is ignore the passage, right? If we just look at this, there's a compound here, there's some kind of flow chart, there's some kind of figure, there's a table, there's another table. Okay, I'm not going to read this. I'm straight up not going to read this, right? And we're going to see what happens, right? Let's just dive into the question. Question number 1. What is the hybridization and the bond angle of the central carbon in the C-C-N bond in citalopram? Okay. I see that there's a picture of citalopram on the side, right? But they just gave me this in the question itself, right? They gave me this in the question itself, and this is enough to solve this problem, right? If you know what hybridization is and bond angles are, right? At least they told me, okay, this is the bond, right? So the central carbon in this bond is the one, in the center, right? Right here, right? So is anybody up to date on their orgo? Does anyone remember the bond hybridization? SP, SP2, SP3. Do you guys remember what that stuff represents? So an SP, right? So let's go through it, right? An SP is something that, so hybridization basically refers to kind of how many bonds an atom has, right? So if a carbon is triple bonded to something, right, then it's overall got 2 regions of hybridization, right? This one in the middle here, and then this one off to the side, right? The hydrogen and the other carbon, so 2 regions. Or it could be something like this. Right. Okay. Or it could be the typical methyl. So the difference between these three situations, bonding situations, is that they have different hybridization, different hybridizations, right? If it looks like this, it's referred to as sp. If it looks like this with 3 substituents, it's referred to as sp2. The reason it's not sp3 is because it's got s and then 2p orbitals. It's an s orbital and a 2p orbital. So that's a total of 3 orbitals. That's a total of 3 bonds. You can think of it that way. Then this is sp3. So that's an s orbital, 1p orbital, 2p orbital, 3p orbitals. So that's a total of 4 orbitals for 4 substituents, right? So what is the hybridization and the bond angle of the central carbon in the C-C triple bonded to N bond, right? Into citalopram, right? Well, what are they showing us here, right? This carbon is attached to how many substituents? This carbon right here. 1 substituent? Which one is the 1 substituent? Okay, good point. There is 1 bond to C and 3 to N, right? But the question is, how many substituents does the central carbon have? And when I say substituent, I mean how many atoms is it attached to? And in that case, the answer is 2, right? So when we talk about hybridization, it doesn't mean how many bonds does it have. Every carbon is going to have 4 bonds because carbon has 4 valence, right? Every carbon wants to have 4 bonds. This carbon up here has 4 bonds. This carbon here has 4 bonds, and this carbon here has 4 bonds. They all have 4 bonds, but the number of substituents, the number of atoms that they're actually attached to is different, right? Because this guy has 1, 2, 3, 4, whereas this guy only has 1, 2, despite them having the same number of bonds, right? So in this case, the C-C triple bonded to the N gives us, we have 2 substituents. So if we have 2 substituents, which one is it? Is it sp, is it sp2, or is it sp3? It's sp, right? Because we have 1 and 2 substituent. Oh, sorry, I should just draw it. We have 1 substituent here and 1 substituent here. So it's sp, right? So immediately we get to delete 2 options, right? As is the case with all of our questions, right? We immediately get to remove 2 questions. Now the question is, they're asking about a bond angle, right? A bond angle, 120 versus 180 degrees, right? So bond angles are kind of self-explanatory, right? If you look at the angle between this H and this C, right? Does it look like 180 or does it look like 120, right? If we compare between these 2 angles. It's 180, right? Because if you look at this as a circle, right, it's half of a circle. And if a circle is 360, then half of a circle is 180, right? Whereas in sp2, we can see that it's a circle split 3 ways. So it's 1, and then 2, and then 3, right? So this gives us a bond angle of, I didn't draw the last one properly, but each of these would be 120, whereas this one is 180. So overall, that gives us the answer of C. Oh, solution is up here. Yeah. Okay. Does that make sense? So notice how we haven't read the passage yet, and we answer the question based on knowledge of what hybridization and bond angle is, right? So let's keep going and see how we can continue to navigate without even like processing the passage yet. Okay, 2. What properties would be expected to be identical between R citalopram and S citalopram? And we've got boiling point, IR spectrum, rate of reaction with the same achiral reagent, and rate of reaction with the same chiral reagent. Okay, so at this point, it's like, maybe we should read the passage a little bit, right? But before we do that, right? Do you guys remember what R and S is? What is that? Anybody remember what that is supposed to be? R citalopram and S citalopram. Well, R and S is referring to the referring to enantiomers, referring to stereochemistry. So it's talking about it's talking about chirality. So enantiomers are compounds that are mirror images of each other. So if we look at the passage real quick, right? We have R and we have S. And the difference here, does anybody see the difference between these two? They look almost identical, but there's a slight difference. And the slight difference is right here. This notation means if it's a wedge, if it's a solid line, a solid thick line means that it's coming up out of the page, and a dashed line means that it's going into the page. So if you were to see this in 3D, this whole part would be flat, this part would be sticking out of the page, and then this part would be going into the page downwards, right? But on S-citalopram, this is reversed. This guy is actually going down into the page, and this thing is sticking straight up out. So this is why, so they are mirror images, because all the connection is the same, but they're mirrored. So because of that one difference, right? The question is that one difference, what does it do, right? What does it actually lead to? And the interesting thing is, right? Again, all that we've gotten from this passage, right, is the idea that these guys are enantiomers, that they're mirror images, right? And now this question is now solvable, even without reading the rest of the passage, because properties of enantiomers is something that you would study beforehand, right? From studying enantiomers, you could know that enantiomers have almost the same chemical properties, right? Because if you think about it, it makes sense. They are the same exact compound. It's just a slight difference, right? A slight difference in its chirality, right? So if they're almost the same exact compound, would their boiling point be the same? Yes, right? And we can even see that all of these choices have the answer 1. So obviously, we don't even need to consider 1. But yes, their boiling point would be the same. If they're almost the same compound, then their IR spectra would be the same, right? Now we have this question, right? These are two different things that are almost the same. So one of this has to be right and one of these has to be wrong, right? They're saying the rate of the reaction with the same achiral reagent versus a chiral reagent, right? And now it's like, okay, well, which of these will be identical and which of these would not be identical, right? The difference between these guys is based on chirality, right? Chirality being the stereochemistry, right? How this thing is structured in 3D space. So since the only difference between them is chirality, then the only thing that could not be identical is a reaction with a chiral reagent. If they're reacting with the same achiral reagent, if it's achiral, then the chirality of the citalopram would not come into play because it's not dealing with a chiral reagent. A chiral reagent bonding to another chiral reagent would have different interactions because the chirality, because how do I explain this? Since this is achiral, so let's just say that there is some random reagent, right? If the reagent is achiral, when it bonds to R versus when it bonds to S, it can't see the difference. it cannot tell that there's a difference between R and S because it's an achiral reagent. It's not sensitive to the chirality. But if it's a chiral reagent, it can detect the difference between R and S. And if it can detect a difference, then it could have different rates of reaction. So this is the only option that could not be identical. So therefore, the properties that would be identical are 1, 2, and 3. And so since it's 1, 2, and 3, it's A. So I'm sure that this is confusing because you haven't reviewed chirality and stuff. But my point is that once you have a strong enough foundation of the material, then reading the passage becomes a waste of time. And even if you read through this passage, it wouldn't help you to understand like that the chiral reagent is what could have a difference in this situation. So it really helps to if you thoroughly understand the material, you're going to save so much time when you do this because you don't need to slog through the passage, because just from understanding enantiomer and chirality, that gives you so much information. Just by this whole passage, this whole front part could be replaced by these are enantiomers of each other, and that tells you so much information. So that's exactly what I'm saying. This could be replaced by the whole thing. R citalopram and S citalopram are enantiomers, non-superimposable mirror images of each other. Enantiomers have almost identical chemical and physical properties in a symmetrical environment. Since enantiomers have different orientations, they would likely not react similarly with another chiral reagent. Therefore, the following properties would be expected to be identical: boiling point, IR spectra, and rate of reaction with the same achiral agent. Okay. And if you have any question at any point, just post in the chat or stop. Okay. Which of the following molecules correctly represents RR tartaric acid? All right. This again, if you look in the passage trying to find something about this, right? There's nothing that's going to help you, right? This is purely asking you, hey, do you know how to measure or how to determine this chirality thing, right? Do you know how to determine R and RR, right? So if you don't remember, it's something called the Kohn-Ingold prelog system, where you look at to determine if a carbon, so here's a carbon, right here, there's a carbon, and this carbon has 3 different substituents. It has an OH, it has a COOH, and it has an H, right? And it also has this thing all the way down here, right? But by looking at these substituents, we can determine the directionality of the carbon, right? So first we're going to rank them, right? What is the highest priority atom that the carbon is attached to? Is it the hydrogen, is it the carbon, or is it the oxygen? What's the highest priority atom here? You can also think of it as like, what's the most electronegative carbon? Is it the hydrogen, the carbon, or the oxygen? The oxygen is the most electronegative atom, right? Compared to it is more hungry for oxygen than carbon and than hydrogen, right? How will we know this, right? How can we tell what is a electronegative and what isn't, right? Well, we have a handy dandy periodic table available to us at all times during the MCAT, right? And the trend is the electronegativity trend. That's something that you're going to learn and memorize as well, is that electronegativity increases going up this way and going across this way. So oxygen is one of the most electronegative elements, right? And then carbon, and then hydrogen, right? So that's how we could rank these atoms. So that would allow us to rank oxygen as 1, the carbon as 2, and the hydrogen is 3, right? So now when we the way that you determine is this R or S is you kind of draw an arrow going from 1 to 3. And if the arrow is going counterclockwise, it's an S, but if it's going clockwise, it's an R. So if it goes clockwise, it's an R. And if it goes counterclockwise, it's an S. However, there's one part of this that I didn't mention, and that this rule applies when the hydrogen is on the dash, not when it's on the wedge. So you see here that the hydrogen is on a dash. So let me go through that one. So when the hydrogen is on a dash, right, let's count the numbers. The oxygen is 1, the carbon is 2, the hydrogen is 3, okay? Let's draw from 1 to 2 to 3, okay? So our arrow is going counterclockwise, right? Our arrow is going counterclockwise. If our arrow is going counterclockwise and the hydrogen is on a dash, this is S. However, in this case, the hydrogen is not on a dash, right? It's on a wedge. So we have to flip our answer. It looks like it's S, but it's actually R because the hydrogen is on a dash. It is on a wedge, sorry. So for example, we can look over here. The oxygen is 1, the carbon is 2, the hydrogen is 3, right? We draw our arrow 1 to 2 to 3. It looks like it's R, and it is R because the hydrogen is on a dash and it's not on a wedge. So we see that this carbon is R, and then this carbon is actually also R. So then this is the correct answer, actually, because they were asking which of the following molecules correctly represents RR tartaric acid. I don't know what tartaric acid is. I don't really care what tartaric acid is. I know all they wanted me to understand was, how does RR work, right? So if you had time, you might like count up, like, is this C4H6O6, right? But if you look at all of the choices here, all of them look very similar. So structurally, it seems to be the exact same across the board. So understanding like what concept am I being tested on is very important for you to be able to kind of fly through a problem really quickly. So again, if you're confused about this, that's okay because you haven't reviewed it yet. But my goal here is to show you that each question is testing you on a specific concept, and it's not necessary that you need to go look in the passage to try to figure it out, right? That's not where you're going to find the answer. The passage is just giving you context. The answer is coming from your own understanding of the concepts. Okay. So next up. In table 1, which is the best solvent for the scientists to use to separate the diastereomers? Okay, so finally, we're being forced to refer to the passage, right? They're telling us to go look at table 1. All right, let's go look at table 1. And, obviously when you're looking at a table, right, you want to understand, it says solubility results for crystallization experiment using different solvents, okay? So let me see if I can understand a little bit about what's going on here. The scientist proceeds, so you said a scientist decides to separate R-citalopram and S-citalopram using the chiral resolution scheme above. RR tartaric acid was chosen as a resolving agent. This method used to separate the resulting diastereomers is described below. The scientist proceeds to select a solvent. A small amount of solvent is added to the solid diastereomer mixture at a room temperature in test tube and stirred, room temperature. Then the test tube is heated in a hot water bath to a temperature close to the boiling point of the solvent and stirred, hot water bath. The results of several trials are presented below. And eventually the scientist successfully separates the diastereomers and the enantiomer. So we see that he tried 4 different solvents, A, B, C, and D. And at room temperature, there was no solute visible. And in the hot water, there was also no solute visible for A, right? For B, there was no solute at room, but then visible in the hot water. for C, there was no solute visible. There was solute visible at the room, and no solute visible in the hot water. And then for D, there was solute visible in the room temperature and solute visible in the hot water. So this question is asking, what's the best solvent for the scientists to use to separate the diastereomers, right? So now let's think about this. Even if you don't know anything about this, right? Even if you've never heard of this in your life, right? Let's really think about this. The scientist wants to separate the diastereomers, right? Separate the diastereomers. And between these two, between all four of these, right? Remember, always think of which two are the weakest, right? There's two significant sets, right? There's A and D, which which stay the same, right? No solute, no solute, solute, solute. So A and D stay the same, whereas C and D are different, right? C and D go from no to solute or solute to no solute, right? So C and D turn different, whereas A and D stay the same. If you want to separate the diastereomers, do you think it should stay the same or should it change? If you want a separation to occur, should there be a difference or should there be static, no change? A change, right? There should be a difference, right? Just in terms of logic, we want to separate things, right? So there should be a difference in the environments for there to be a separation. So right away, that helps us understand, just from a logical standpoint, right? That helps us to understand that A and D are not it, right? Because we want there to be a difference. Now we come to the harder choice, right? The choice of, well, should the solute be visible and then not visible, or should it be not visible and then visible, right? And so here is where you would kind of need to have a little bit of understanding about what the scientist is actually doing. And this is actually a purification technique called crystallization. I'm going to show you that how crystallization works. Crystallization is basically when you have an impure compound, right? An impure compound, you can put a solvent in it and then heat it up. When you heat it up, the solute that you care about has dissolved completely into the solvent, right? But once it cools down, it will start to crystallize, right? And all of the impurities that were in the compound remain in the solution, in the solvent, whereas what you wanted will crystallize out as it cools down. So, and it will crystallize out in a more pure form. So the question is, this person wants to separate the diastereomers out. So if he wants to collect crystals of diastereomer, should the solute or the crystals be visible at room temperature or in the hot water bath, right? If we try to understand what this process is, we have an impure compound at room temperature, we heat it up so that it dissolves, right? And then after it dissolves, we heat it up so it dissolves, right? And then when it cools down, it purifies and forms more crystals, right? So the question is, should the crystals form at room temperature or when it's really hot, right? According to this, do the crystals form when it's room temperature or when it's really hot? When it's really hot, the crystals melt, right? When it's really hot, the crystals melt. When it's room temperature, the crystals come back. So in this case, it's better if the solvent that allows the solute to be visible at room temperature is the better choice. Because when you heat it up, it will be invisible, right? It will be dissolved in the solvent. Then when it cools down to room temperature, it will become visible. And that's going to allow the scientists to separate the diastereomers from each other. So this is again, these are all concepts that you have to learn. And once you learn them, right? And obviously when you tackle a problem and you think about it and you're like, okay, I don't get it, but I'm going to try to understand this now, right? That kind of motivates you to understand it, right? Because you have a problem that you're trying to solve. So you truly have to understand, what you're thinking about the concept, right? So in this case, it's better if the solute is visible at room temperature, because once the solvent cools down, once a hot water bath cools down, these crystals are going to form. These visible crystals are going to form that can be extracted from the solution. So crystallization aims to exploit differences in solubility between the compound of interest and impurities that may be contaminating that compound. It is difficult to continue to experiment if the solute dissolves in room temperature, because then the temperature of the solution will need to be lowered to below room temperature. The solvent and solute mixture is usually heated to a high temperature and then allowed to cool slowly, so the crystals of the compound of interest can gradually precipitate out of the solution above room temperature. So that gives us the best solvent of C. The solutes do not dissolve at room temperature, but dissolves at a higher temperature. So then the compound of interest may precipitate out of the solution as the temperature is gradually lowered to room temperature. Okay. And lastly, we have the question, based on the log p-values provided in table 2, what general assumptions can be made about citalopram's properties as a drug in the human body? Okay, well, table 2, I got to go read what table 2 is, right? So table 2 is various compounds and a log p. But what is log p, right? So we look at the previous paragraph. During a search, he comes across a log p value, which predicts the polarity of a given compound. Oh, interesting. Polarity. Okay. So log p, log polarity. Compounds that dissolve in organic nonpolar solvents have higher log p values. And so then the opposite would be, so compounds that dissolve in aqueous polar have a lower log p value. Okay, so we got that, right? So we can write, and they're asking, based on the log p values provided in table 2, what is a general assumption that can be made about citalopram as a drug in the human body? So if you look at the citalopram log p, it's 3.58, right? So what did we learn about log p? They said log p when high, so high log p is equal to nonpolar and organic, right? So we just found out that citalopram has a high log p number of 3.58. So therefore, we know that citalopram is also nonpolar and organic, right? So now they're telling us, now the question is, what general assumptions can you make about it as a drug in the human body? And then there's a hint here. So let's try to read the answers. The answers are saying lipophilic with a low volume of distribution, lipophilic with a high volume of distribution, lipophobic with a low. Okay, so this is a classic style of question, right? Where this is two things that are being asked first, right? There's two parts to this question. The first part of the question is it lipophilic or is it lipophobic, right? And then the second part of the question is, within that, is it low volume or high volume? So first, let's tackle this. Lipophilic versus lipophobic. What does philic and phobic mean? Yeah, phobic repels, right? And philic attracts. Perfect, right? We have phobia, fear, right? So what does lipo mean? Lipo. You may have heard of liposuction or that's actually the only word I can think of starting with lipo. But what is a liposuction, right? It's a surgery that gets rid of fat, right? Exactly, lipo, right? So this is saying fat liking versus fat repelling, right? So if they said citalopram is nonpolar organic, are fats nonpolar or polar? They're non-polar, right? They are long carbon chains. Long carbon chains. The carbon chains are not polar. They're hydrophobic, right? So fats are non-polar organic. Therefore, citalopram is going to be lipophilic or lipophobic. Citalopram is nonpolar. Fats are nonpolar. So is citalopram attracted to fats or repelled from fats? It's attracted to fats, right? So it's philic, right? So again, that lets us cross out two choices. And now we need to understand this concept, volume of distribution, right? And we never heard of this. And they told us in pharmacology, volume of distribution is a theoretical measure that tries to estimate how much drug gets absorbed into tissue. So the question is, would this be highly absorbed or not highly absorbed into tissue, right? So now you can see how this section is kind of a mishmash of everything, right? Because this is a chemistry physics section, but you're getting a biology question, right? You're getting a little sneaky little biology question here, right? This is lipophilic phobic. This is all biology stuff, right? So this chemistry physics section, right? You can see that they're using numbers, right? They want you to understand numbers, but in the context of all these biology and biochemical concepts, right? So now we're thinking purely conceptually about, what does it mean for a drug to get absorbed into tissue, right? And so now the question is, right, we're talking about lipophilic, we're talking about fat loving, right? So the question is there fat in our tissue? Is there a lot of fat tissue in our bodies, right? This is purely just a question of like knowing or not knowing, right? Like, do we have fat in our bodies, right? And the answer is yes, we have fat stores, right, in our tissues, right? And that's how we store energy, right? So if this drug has a high degree of non-polarity, which means that it has a high degree of lipophilia and it is very attracted to lipids, right? Therefore, it's very attracted to fats. Therefore, it gets very absorbed into tissue. Let me just write out that logic, right? We said a high log P is equal to non-polar is something non-polar, right? So therefore, and since citalopram has a high log P, therefore citalopram is non-polar. Therefore, citalopram, and since we know that fat is non-polar, right? Since fat is non-polar, citalopram likes fat. And then since fat is in our tissues, citalopram is highly absorbed into our tissues. So this is step by step what they wanted you to understand, right? Understand what does log P mean, understand how it relates to citalopram, understand how that relates to fat, understand how fat relates to our biological tissue, right? So this seems like a lot, but these are just like basic facts that you're going to pick up when you're studying, right? And that's why if you get one thing out of this, it's like the breadth of the content, right? How wide it is, but it's not that deep. It's just this particular fat. Oh, there's a lot of fat in our tissues. Oh, lipophilic means fat loving, right? So it's a mile wide, but it's only an inch deep is the best way to think about it. So that tells us that, the logic that I explained to you now helps us understand that that it's lipophilic with a high volume of distribution. Okay. So let's see here. All right, so yeah, so that is the end of the chemistry and physics review. We talked about how to understand units. We talked about how to tackle a passage. And we talked about how to manipulate units for an equation. And next time we will talk about either biology, biochemistry, or psychology and sociology. I'm not sure which one we'll do first, but one of those two. Okay.